Thanks, Ryan. So I see that it's still like 8:59. So let's wait for a few more seconds.
Yeah. So it's now you are in charge. You can start by saying like welcome everybody and things like that. Now over to you completely.
Yeah, we are already on YouTube, right?
Yes, it's already being
Yeah,
streamed
it's
live.
started.
Okay. Yeah. So welcome all to the fourth day of the conference. And the first speaker will be Professor Sunil Mukhi from ISET Pune. We'll be talking about classifying RCFTs. Over to you, Sunil.
Thanks, Prithvi. You'll need to speak louder, by the way. Huh? You were just barely audible.
Okay. Okay.
Yeah.
Yeah.
Okay. Shall I share my screen?
Yeah. Correct.
Now let's see here. I guess this is it. How does this look? Visible?
Yeah, I can see your pointer also. Can you move your pointer once?
Pointer?
Yeah.
Yeah.
Everything is okay.
Okay, I'll full screen it now.
Yes.
Very good. Okay, well, very happy to be here, and I thank the organizers for inviting me to give this talk and for organizing this very nice conference, which is running over all kind of different time zones. So it's a bit of a challenge to follow, but I've tried my best within my teaching duties to follow most of the talks. So I actually have, I'll start with confession. I've changed my title, but then I didn't want to annoy the organizers. So I kept the old title in small print, but the actual title is Self-Dual Lattices, Cosets and Rational CFT. And this is kind of a brand new talk, so which I really spent time preparing yesterday and day before. And I don't know if it will be useful to you, but it's quite useful to me because I didn't organize my thoughts on this particular topic in this way till I made the talk. So one good thing about this new title is that I won't have to repeat things which I've been discussing for the last 2 years and which certainly the most of the Indian audience has heard at least once before. Okay, now, yeah. So this talk is based, so I have a bunch of different papers, but the 4 papers which I've picked out for this talk start from 2016, 2 papers, one of them with Matthias Gabriel, and both with my master's student Harsha, who is now at Brandeis doing his PhD with Albin and Matt. And then 2 more papers with my other master's student Ramesh Chandra, who is now at Amsterdam doing his PhD with Eric and Jan. So, and there's a lot of other work, including older work from the 80s and work from more recent times with other students who I've listed at the bottom. And basically, I'll summarize the main result of the first paper and then tell you what in the other papers sheds more light on that. Okay. Now, current interest in 2D conformal field theory comes and goes. It became popular in 1984 because of a coincidence, BPZ coming at the same time as the first superstring revolution. So suddenly string theorists got motivated, but also condensed matter people were sucked into this because it describes phase transitions. And of course, it's a beautiful mathematical structure. But current interest is related to ADS CFT, and therefore, actually, it centers on what we call irrational or non-compact CFT, which are quite generic CFTs with conformal dimensions that are not necessarily rational, and a number of characters not necessarily finite, central charge large. And the reason is that these should be dual to semi-classical gravity in 3D asymptotically ADS spacetime. And strangely, because it's an easy problem to pose, what is the CFT dual to pure ADS3 gravity? We actually don't know the answer almost at all. We know something about its partition function. What we know also seems to be wrong in some ways. So it's a long history and it's not quite central to my talk. Now, it's not a very generic CFT that people are seeking. people want CFT is dual to pure gravity. So the CFT should not have other conserved currents. If it had other conserved currents, it could be dual to gravity plus gauge theory plus higher spin fields. But of course, that might be interesting, but that's not the thing right away. That's not the simplest problem. Okay, and as I said, no such CFT has been actually found. We have bounds on it, we have constraints on it, a lot of things, but really we don't know what CFT, if any, is dual to 3D gravity. Now, in a different world, occupied by different people with different motivations, we find rational conformal field theories. Unlike the case I discussed earlier, these always have additional conserved currents beyond the stress tensor, and it's the reason why they are rational, because these extra currents organize the partition function into a finite number of generalized characters. So actually they organize the characters into a finite number, and then the partition function is quite a simple sum over the mod squared of characters. Though they have C greater than 1, they can even have extremely large C, and they always have infinitely many Virasoro primaries, therefore, but we don't let that bother us because they're still essentially simple. And simplicity is good from the condensed matter point of view because we want theories with a few critical exponents. The Ising model has basically two conformal dimensions, a half and 1/16th, or double of that actually. And that's enough for that model. Potts has a few more, and like that. Now, of course, these pioneering works, I'm sure everyone here knows about. And these gave us infinitely many minimal series. And then there were this coset construction of the form Wessumino-Witten over another Wessumino-Witten. I should have called this WZW1 over WZW2. That gave us infinitely many families, including, in fact, Virasoro and other minimal models. Now, RCFTs are, of course, quite unfashionable today, and largely it's because they are unsuited for semi-classical ADS CFT, but also because most people think that they are either classified or essentially classified, or at least we sort of know what they do, and that's a space we understand. And it'll be my job to argue that this folklore is quite wrong, and I'll show you examples where folklore is quoted, which is simply not correct. Now, these are two worlds, irrational and rational CFT apparently, but there's an extreme class of rational CFT that still keep cropping up in the literature under names like Monster, Moonshine, Matthew. So these are the so-called meromorphic or holomorphic or chiral CFT. And I'll actually review them in a little detail in a few minutes. These remain popular partly because of their mathematical connections and partly because they are viewed as a pleasant, exotic outlier among rational CFTs, which have interesting properties, but which are thought to be unique to them. Okay, now these chiral or holomorphic or meromorphic CFTs, I'll call them integral CFT or ICFT because compared with rational CFT, these are integral. That is, all states have integer conformal dimensions. There are no fractional critical exponents. Even the central charge is integer. And they're very, very special. And what makes them special is that there's a large chiral algebra. In general, we don't know what it is. And under that, there's just the identity. Everything else is secondary of the full algebra. And so the partition function manifestly has this factorized form. Now, alternatively, one can just pick the holomorphic part of it, chi itself, rather than mod chi squared, and say, well, that's my theory. It has no right movers. It has only left movers. And that's called a chiral CFT. But I'm not going to distinguish these two because if you know the chiral one, you certainly know the other one. And if you know this one, you can take its holomorphic square root and get this one. So when I say chiral or when I say ICFT, it might be either of these. Okay. Now, David Gross actually played a major role in bringing ICFTs to the attention of a string theory audience. I think it's fair to say certainly I had never heard of them before. And reading BPZ, you would not learn about them because they didn't discuss the ICFT property at all, nor Knizhnik Zamolarchikov. But there are two famous ICFTs with central charge 16, and they are crucial to constructing the heterotic string, which of course was David's spectacular invention in 1985, along with Harvey, Martinek, and Rome. Now, the 1980s were also a very fertile period for ICFTs because mathematicians found that they are very closely related to representations of the monster group, which is an interesting group. I'll very briefly discuss it, as well as to codes. Okay, and that relation is still fascinating, and it keeps cropping up both in mathematics and in the physics literature. Okay. Now, I've said that ICFTs do not appear in any minimal series. This certainly tells us that this BPZ or KZ or KZ, I'm never sure whether I should say Z or Z, this scheme based on null vectors and minimal series is simply not enough. It classifies a lot of rational CFTs, but it doesn't get anywhere near the ICFTs. So that's an important thing. There are some kinds of islands, to use a currently popular word, which seem to lie outside this scheme. And what I'll try to convince you in this talk is that, in fact, they're not islands. In some sense, most rational CFTs lie outside this scheme. Okay. Now, how do we generate ICFTs? I'll have a brief review in a minute, but let me just tell you what you probably know. If I have free bosons compactified on a torus, which is defined by an even unimodular lattice, then you immediately get an ICFT. So every even unimodular lattice, and they are quite constrained objects, well studied also, will give you an ICFT. So it's a free boson theory, so that's fun because you can do a lot of things with that. Now, the topic of this talk is that in 2016, trying to explain something, we stumbled on a novel and unexpected relation between general rational CFTs, or by general, I mean quite a large class of rational CFTs, and ICFTs. And this we call the novel coset construction, and I'll explain it.
Sunil, can I ask a question?
Please, yes.
In your classification, where do Gepner models sit?
Where do what?
Gepner models.
Gepner models. Gepner models are supersymmetric, right?
Yeah.
So I should have said, somewhere I'll say it's on my last slide actually. This entire talk is on the assumption that I'm dealing with bosonic CFTs. With supersymmetric CFTs, you have half integer dimensions. So you have projections, you have sectors, Raman, Nevis-Schwartz. So that's a whole story. And actually what I'm saying can, I'm sure, be generalized, but it hasn't been done. According to me, it's a whole open class of problems.
Thank you.
Yeah, therefore, I shouldn't have mentioned Matthew probably, because many of those things are related to elliptic genera, and that's not in this investigation, but it should be. Okay. Now, the construction we found enables us to create entire families of new rational CFTs that are neither integral CFTs nor in any minimal series. And, you could call them exotic if there were a few, but my argument is that they are actually more in number than the ICFTs. Okay. And this opens an important new avenue into the classification problem for RCFT. It makes it worse, obviously. It tells us that there's much more that we didn't really understand in the 1980s. But I think it carries also some lessons for the modern conformal bootstrap people who want to classify more general CFTs. And I'll mention those lessons. Okay. Now, so I've said this, there are many more types of RCFTs than were previously thought, and including very simple ones. If you could generate exotic, very complicated CFTs, nobody would be interested perhaps. But these are very simple ones, simple in the sense that they have a very small spectrum of primaries under a very large algebra, but it's not so small that the theory is an ICFT. And RCFTs, through this construction, inherit properties that were previously thought to be peculiar only to ICFTs. Okay, after reviewing this, I'll talk more about more recent work with Ramesh Chandra, where we use this construction in a non-trivial way. And I'll also talk about a different paper with Ramesh with a totally different theme called quasi-characters that I won't be able to discuss in this talk, but I'll quote the result insofar as it helps us understand these. exotic RCFTs. Okay, with that, I'll put up a brief review. I'm sure most of you know this. This is what the partition function of a 2D CFT looks like as a trace over a full Hilbert space, with L0 and L0 bar being the Virasoro generators. They are modular transformations, so you can map this partition function to a torus path integral that has global diffeomorphisms, and therefore to not have global diffeomorphism anomalies, the partition function should be modular invariant, and that's the statement. Now, I should mention as a small digression that there's a sudden wave of interest saying, let's classify all Z of tau and tau bar. But uh, it's a peculiar thing to say in 2020. There are at least 2 or 3 papers by very well-known people saying, oh, we're going to attempt the problem of classifying all Z and tau of Z and tau of tau and tau bar. Well, that's exactly what the modular bootstrap is. And I think the first attempt was by Samir Mathur, Ashok Sen, and myself in 1988. So it's a 32-year-old problem, and it's not a new problem that was invented this year. But it's, of course, an unsolved problem, and it's quite possible that it's essentially unsolvable because it doesn't benefit from holomorphicity. Okay. Now, this invariance, modular invariance, plays a crucial role in classifying CFTs. And we'll see that this novel coset construction we find automatically gives you modular invariant partition functions. So there it solves sort of that problem from the outset. And that's a nice thing because it can create lots of reliable new CFTs. Okay, now just to define rational CFTs once, they have a finite number of primaries under some not necessarily known extended chiral algebra. That may be a current algebra of spin 1, or it may be a spin 2, spin 3, or any other thing. And there's a character for each primary, which is the set of trace over the only the holomorphic descendants over that. And then once you have that quantity, then the partition function is a sum over the mod squared of these characters. And the sum is over p different primaries, of which I equals 0 is the identity. The others are all non-trivial. As we saw earlier, ICFT is just the special case of this with p equals 1. And there's a theorem essentially that if p is finite, then the conformal dimensions and central charge are rational. And also if p is 1, then the conformal dimensions and central charge are integer. Okay. And characters have this typical power series structure in the parameter q with a leading critical exponent given by this, and then some degeneracies multiplied by powers of q. So this is like a standard partition function. These a's, if they are non-negative and integral, we'll call this an admissible character. Now, characters are not modular invariant, and it's very hard to make them so, except for ICFTs, because they're holomorphic. And being holomorphic and modular invariant is extremely constraining. However, it's enough for them to transform under modular transformations into something like a unitary linear combination of themselves with M dagger M equals 1, because then the sum over chi mod squared will be invariant thanks to this unitary matrix. So they are actually what are called vector valued modular functions, or VVMF. Now, just finding VVMF, which is also a largely unsolved problem in mathematics, is far from being a sufficient criterion, because VVMF turn out to have these kind of expansions where A's can be arbitrarily arbitrarily bad rational numbers. They can also be negative. There's nothing integral about a general VVMF. So in that space, we have to look for special cases and call those possible characters of a CFT. But even if we find those, I will show, and this contradicts some folklore, that the existence of such things does not guarantee the existence of a corresponding CFT. In fact, the family of admissible characters is much larger than the family of actual CFTs, and we'll see that. So I hope these are going to be valuable lessons even for irrational CFT, where some of these properties are implicitly or explicitly assumed, or let's say that that these facts are not taken into account. Okay, I'm happy to pause for questions if any. Okay, so let me move on to a quick review of integral CFT and then go to the novel coset construction, which is the heart of this talk. Okay, so I've indicated that the partition function has this nice mod squared holomorphically factorized form. And if we're just looking for chi's which are modular invariant, possibly up to a phase, we already know the answer. They have to be given in terms of this Klein J invariant, the J function. And you have to take J and raise it to a fractional power, which can only be a multiple of 1/3, and then multiply by a polynomial of J. Okay, and that's all possible characters for rational CFT. So the problem of finding the characters is essentially trivial and solved. P has to be suitably chosen so that it gives an admissible series in Q. J itself is admissible in Q because you see these are all positive integral coefficients. But you know, if I took some weird power of J or some weird polynomial or negative coefficients, I might not get an admissible result. So I have to tune my polynomial accordingly to get it. Okay. Now, J starts with Q to the -1. Therefore, J to the 1/3 starts with Q to the -1/3. And that means central charge is 8 because Q to the minus C by 24 is the leading term of this character. In general, since I'm also allowed this polynomial and any power here, the general statement is that C is 8n. So ICFTs always have central charge a multiple of 8. Let me show you a few known examples. If C is actually 8, there's only one possible character, which is J to the 1/3. It follows right from this formula, which I've just shown you. And it's unique. Okay. If C is 16, then chi is J to the 2/3. That's unique. But there are two different CFTs with different operator product expansions, different fusion rules, different everything else, but the same central charge and the same character. Different correlation functions for their currents and other fields. At C equals 24, however, non-uniqueness sets in. And the reason is that now I can have J. These ones, by the way, are invariant only up to a phase, modular invariant only up to a phase, but J is really invariant. If it's really invariant, nothing stops us adding an integer to it. Okay. And once we add an integer, that integer can be anything, and it's still an admissible character. If you go back to this, the integer only has to be greater than -744. If it's less than that, then this term turns negative. And if it's greater, you know, it's unbounded. So there are infinitely many candidate characters. If you go to C equals 32, it's like this. There are again many. And so in general, there are infinitely many candidate characters starting at central charge 24. Luckily for the heterotic string, luckily or unluckily, we wanted C equals 16 because it's the difference between the critical dimension of superstring and bosonic string. And in that case, there are only two choices, and that's why there are only two heterotic strings in 10 dimensions. Of course, supersymmetric. Okay. Now, all these examples correspond to a number of free bosons equal to C, so that the central charge is C, compactified on a torus, which is RC mod gamma, and gamma is an even unimodular lattice. Now, partition functions on such lattices are well studied. They are lattice theta functions. And if the lattice is even unimodular, then these theta functions go back to themselves under Poisson resummation. And then modular invariance is thereby guaranteed up to a phase which we won't worry about. Okay. So as I said, with one character, it's easy to find all. So in ICFT, it's easy to find all admissible characters, but not all lead to genuine ICFT. So let's focus on C equals 24. This is the general solution. But Shelikins, in a beautiful paper in 1992, which I'm sorry that people don't read because I still think it's one of the most revealing papers about conformal field theory, argued that there are just 71 rational CFTs in this family. And moreover, so therefore, most values of n don't give any CFT. Secondly, he argued that a fixed value of n can give several CFTs. So there are values of n we'll see which give 5 or 6 different CFTs for the same n. So there aren't even 71 values of n. There are something like 40 values of n or 35 values of n, maybe even less actually, which give all the 71 CFTs. So this phenomenon that multiple CFTs can have the same character replicates at c equals 24 and is perfectly generic in ICFT. He also showed that you can generalize ICFT beyond lattice theories using orbifolds and other nice constructions. I won't go into that here. One of his ICFTs, which was known before his paper, of course. So Schelikens classified all known and then completed the classification. One which was known is the monster CFT. In that one, n is actually minus 744, so it saturates this bound. And except for that one, all the others have underlying Kac-Moody symmetries, and their partition, their character is a special modular invariant linear combination of those, which is quite remarkable, and I'll show it to you later. Okay, so this is the monster one, and I think I'm repeating myself here. And this was actually a discovery of late 70s, mid 80s. So it was happening during the heterotic string or the superstring revolution. It has no Kac-Moody algebra. Its states fall into representations of the monster group, which is the largest finite simple group, sporadic finite simple group, not belonging to any series. And this is its order, number of elements. And in 2007, Witten had actually suggested to use a generalization of the monster at large central charge called extremal CFT to be holographically dual to pure gravity in ADS. So we circle back to a problem I started with. But nobody could find these extremal CFT, and there were arguments, notably by Matthias Gabriel and collaborators, that they may not exist. I don't think those arguments are watertight, but so one could still reopen the question. But also, nobody believes that ICFT can describe ADS3 gravity because it simply doesn't have the properties to describe a semi-classical gravity theory. It doesn't have the usual, you expect a very irrational theory to do this job. Okay, good. Now, ICFTs are thought, I've said this before, thought to be very special and have different behavior from generic RCFTs. And I'd like to give you an example from the literature, which is a paper by well-known authors, which I'm not going to quote because I don't agree with them, and I've told them so also. This recent paper, which is still up on the archive, says that current wisdom tells us that other than ICFTs, all known candidate modular invariant partition functions actually do correspond to CFTs, and distinct CFTs cannot have the same partition function. And these two statements are entirely incorrect. And I'll prove that at the end of this talk. I'll show that the second comment is just disproved by the novel coset construction. And the first one also is disproved by a different paper of mine, where I'll quote the result. So it's quite generic for rational CFTs to be distinct and have the same partition function. It's quite generic for admissible modular invariant partition functions to not correspond to any CFT. So these are two important lessons. Okay. And the bottom line is that large families of quite general non-holomorphic rational CFT can share properties with ICFT. They are not as different as is generally thought. Even more strong statement I'll make is that we don't know most rational CFTs, and the ones we do know are a very special space, subspace. Okay. So with that very, very long introduction and review, it'll be quite easy to describe the novel coset construction. So I'll continue to the rest of my talk. But again, this is a good point for questions.
Sunil, hi.
I'm so glad you're there. I thought everyone had gone home.
I was just wondering what prompted the authors to make such a strong claim. I mean, was there some attempt at a justification or something? I mean,
I didn't find any. They have, they have a short paper and a long paper. I'm probably giving away the authors, but I didn't find any. And I wrote to them, and they said, no, no, you're right. We'll look into it and revise the paper. So they didn't offer any justification, but it's still up. They haven't revised it in a few months. So we could discuss this. I'd certainly like to know what they had in mind.
No, I meant, is there maybe if you put additional restriction? I mean, there are ways of making statements true by putting in enough caveats, enough
So here it is. So here it is, of course. If you look at the BPZ or KZ or coset model, old coset model minimal series, then it's probably true. So I think in the minimal series paradigm, it's probably true.
Yeah, by kind of, I mean, but that's an old, in a sense, it's just.
I'm glad you brought it up. I'll be very happy to discuss this with you offline, because I want to know really what they had in mind, and maybe I'm missing something.
Okay.
Of course, they then go on to say that this folklore is wrong, but my point is it isn't folklore. At least not as far as I'm concerned. Okay.
Okay. Sunil, could I also ask probably very stupid question? I had the impression that in the 80s, people were heading towards what they thought of as a classification program for rational CFTs.
Yes.
These papers, Seiberg and Moore and so on.
Yes.
So that program never reached any conclusion?
No, that program gave conditions that a rational CFT should satisfy, and said, I think it essentially said that if you find anything which satisfies these equations, these polynomial equations and so on, then it's a rational CFT. But, it's not a very constructive classification program. And I looked through Greg's review talks on it quite recently, and I didn't find them discovering a single new rational CFT, for example, or telling us what the space looks like. So I would say that, you're right. I mean, that's the paper which seemed to close the subject for most people. But I think it set down criteria, but you can always set criteria. I think there's a difference between criteria and classification. I hope Nati isn't here to yell at me, but this is what I think.
Right. So there was no explicit listing of RCFTs.
Well, classification is a very loaded word. Like, classification should tell you, what to do if you want to find something. Supposing I told Greg and Nati that I want a theory with a low central charge, but only two primary fields under an extended algebra, I don't believe they would have any way of finding it.
Okay. Thank you.
Okay, so now let's look at this novel coset construction. And here it is in one line. What we defined was the coset of an ICFT by a Wessumino-Witten model. That's all it was. It's that simple, and it's almost like something we already know. The thing we already know is coset of a Wessumino-Witten model by another one. This was Goddard, Kent, Olive, famous result from 1985. And what they showed was that because both of these are minimal series, if you take the quotient, you get another series, and it can have different symmetries because there's, the current algebra of the numerator will be broken by this quotient to a sub algebra or to nothing even. And you can reproduce Virasoro minimal models, WN minimal series, and lots of minimal series. And I think this was more than Moore and Seiberg. This was the thing that made people feel that, well, if we want a CFT, this is what we have to do. Now, an ICFT is not a Wessumino-Witten model, except in very rare cases. So E8 and E8 cross E8 are rare cases where it's both ICFT and Wessumino-Witten model, but most generally that's not the case. In fact, those cases are very rare. So this is a different coset construction from this, similar in spirit, but different in outcome. And it's actually much simpler because ICFT is much simpler than a generic Wessumino-Witten model. Okay. Now, so what we do here is to start with an ICFT associated to, for example, free bosons on an even unimodular lattice, and then quotient in a certain way, which we showed by a Wessumino-Witten model. And this creates typically a finite family of CFTs C, whose parent is the ICFT. So in some sense, these are CFTs with a common parent. Okay. Now, let me just show you a few examples. I don't know how illuminating this table will be, but let's just go through it. On the left are some simple Wess-Zumino-Witten models that Samir, Ashok, and I stumbled on in the 1980s as being the simplest Wess-Zumino-Witten models. They each have two characters, and they are based on SU2, SU3, G2, D4, etc. I've talked about this a lot. Their central charges range between 1 and 7. Okay, now we can take theories from Shelikins's paper, which have central charge 24, and many of them have a Kac-Moody algebra, which is a direct sum, but which includes one or more of these algebras. So we can quotient then this corresponding Shelikins theory with the left side theories one by one, and we get the theories on the right side. And the central charge, if we quotient a theory with central charge 24 by something with C equals 1, we get C equals 23. It just subtracts. For 2, we get 22. So these are pairs. This is the denominator of the quotient, and this is the numerator. This is the new coset theory. The new coset theory has these conformal dimensions. It has these Kac-Moody algebras, which you could, I suppose, if you spent years on a desert island, you might stumble on these theories by finding a modular invariant based on these. But this way you get these theories directly, and they have only two primaries, the identity and a primary of dimension H tilde. So this is an example of novel cosets. And in fact, we already knew these these theories as conjectures arising from an older paper of Nakulich as well as a more recent paper of mine. And our novel coset construction showed that these things which produced these characters which were known are actually CFT. So this is an example of that wrong statement I quoted earlier, where finding characters, it turns out that they do correspond to CFT. It can happen, doesn't always happen. We also know when it doesn't happen. In this case, it does happen. So conjectured characters conjectured in these papers turned out to be RCFT with central charges in the range 16 to 24. Okay. And as I've said, these have non-simple Kac-Moody algebras. I hope the notation is clear. A, B, C, D, E, F, G are the Lie algebras. And first index is the subscript is the rank, and the second is the level K. Notice that even F and G type Kac-Moody appears here. So it's not only the simply, and B type. So it's not only simply laced. Okay. Here's a more complicated list. This is with 3 character theories. And this also is from the paper with Gabriel. These are the previously known Wess-Zumino-Witten models. And these are a set of new theories with central charges between 14 and 24. And well, one can work, they have 2 primaries besides the identity, and one can work out everything, their partition functions, and anything else we need to know. I should say that mathematicians working independently along other directions stumbled on many, but not all of these. And so it was, and they claimed that these were what you needed to complete some classification scheme of theirs. So we were able to point out to them that we had these earlier, but also we had more than the ones they had stumbled on. So this is very powerful. So they were discovered later on in the maths literature using different methods. Okay. Now let me just summarize some key features and then go on to something interesting, and then more interesting, and then tell you what we learn. Because this is a coset, the central charge of the Wess-Zumino and the coset theory add up to the central charge of the ICFT, which is a multiple of 8. Turns out the conformal dimensions of the Wess-Zumino and the coset theory also add up to an integer. It's actually very pretty because it says that the Wess-Zumino with its coset together generate the currents of the ICFT. So ICFTs are famous for having exotic high spin currents, and these high spin currents turn out to be composites of primaries of the Wess-Zumino-Witten theory and the coset theory. Finally, this relation, which subsumes both of these above, says that the character of the ICFT has a bilinear relation with the characters of Wess-Zumino-Witten models and the characters of these novel cosets. So in a way, we've inverted this relation. If you look at this relation, it's C equals ICFT over WZW. We can write this as ICFT equals C times WZW. Take this WZW to the other side. And that's what this equation is telling us. So this is WZW, this is the coset C, and this is ICFT. And this bilinear relation is holomorphic. That's wonderful, because it says that you have pairs of CFTs with the same modular transformations such that if I dot their characters, I get a modular invariant. Okay, good. Now let's move on to another case, and it's quite interesting. So, you know, after Shelikins's paper, an obvious thing to do was to, yes, please.
Yeah, I mean, you might have explained this to me earlier also, but this when you do the coset, you normally sort of take the denominator and the currents in the, I mean, you're kind of identifying. So you're saying you pick a subset of these higher spin currents in the ICFT, and that's what you're kind of gauging when you do this coset.
No, we're gauging actually the cuts. So these ICFTs in general also have spin 1 currents. The only ICFT which doesn't have spin 1 currents is the monster. All the others do have spin 1 currents.
Okay.
So
but they form like a Vesumino. I mean, they form a Kac-Moody, non-abelian Kac-Moody.
Non-abelian Kac-Moody algebras. The only thing, so I'll explain this in a little detail actually in about 2 slides. So
okay, then we can talk.
It will become hopefully clear in 2 slides.
Okay.
Okay. So following Shelikins's paper, one may have thought, well, he's classified all ICFTs in 24 dimensions. Let's go on to 32, which is the next case. Unfortunately, there are 10 to the 10 even unimodular lattices in 32 dimensions, while in 24, there were only 24. So Shelikins took 24 as the base and added an order of about 50 theories to get 71. Those theories are orbifolds of these theories with a few, you know, adding some vectors to the lattice and things like that. But, you know, you're starting with 10 to the 10 known theories and then trying to complete the classification is pretty much impossible. So Shelikin's paper is also in some sense the end of that particular project, which is sad in a way. So the analog of that paper has not been written for C equals 32 and presumably never will be. And actually interest in ICFT from that perspective essentially stopped when people realized that. But we are not interested in a complete classification here, at least for this talk. 132 of these 10 to the 10 are very nice. They're called Kerr-Ware lattices, and they have what are called complete root systems. And what a complete root system is the following. Whenever you have a point of length squared 2 on a lattice, that corresponds to a current because its conformal dimension is half alpha squared, where alpha is that vector. So if alpha squared is 2, then half alpha squared is 1, and you get a current. So the current algebra is generated by the root system. Now, of course, there are abelian currents are generated by del x, where x are the scalar fields. So those have to be added. This is how lattices generate current algebras in the first place. How do you get E8 out of an E8 lattice? What I'm telling you is the way. But a complete root system says essentially that the root system spans the dimension of the lattice. And another way of saying it is that the total central charge for the Kac-Moody algebra is equal to the dimension of the lattice. In general, it's less than or equal to. So for most of these, it's less than, but for 132 of them, it's equal. And that makes them much more tractable. And so we worked with these, and I'll show an example that will make my point clear. So we'll take the coset of such a lattice CFT by any of the Vesumino-Witten theories in the MMS series, which I showed you earlier. And the advantage of a complete root system is that once you take the coset, you can determine the full Kac-Moody algebra and from it, the stress tensor. What happens if it's not a complete root system is that you can get the Kac-Moody algebra, but the stress tensor can have other contributions not coming from the Kac-Moody algebra. And that becomes much more difficult, and it's an open question. Anyway, so for this set of 132, which is enough for us to make some points of principle, we could find one or more new CFTs for every Kerr-Ware lattice. And we found that they have central charges in the range 24 to 32, but they still have only 2 characters because we took the coset by Vesumino-Witten theories having only 2 characters. So these cosets have 2 characters and central charge in this range. Let me show you an example which will also help with Rajesh's question. So there's a lattice whose complete root system is A2 to the 16. A2 is SU3, and SU3 as a Kac-Moody algebra at level 1 has central charge 2, the rank of SU3. And 2 times 16 is of course 32. So you can recognize that this is a complete root system from the fact that the total rank of this algebra is equal to 32. In general, it's less, as I said. In curve-ware lattices, it's equal. Okay, now there's a bit of fun. The curve-ware lattice, as it's given to you, is not unimodular. You have to do some tricks of adding few vectors from the dual lattice, but there's a way of ending up with a unimodular lattice. And then you have an ICFT, and then you have its quotient. Okay, now how many currents are there in the ICFT? Well, SU3 has 8 currents, the dimension of SU3. 16 of those have 128 currents. Okay, now we can actually construct the character of this theory in the following way. SU3 at level 1 has 2 characters, chi0 and chi1, but SU3 to the 16 has all possible two primaries, chi0 and chi1, and this has all possible combinations, chi0 to the p, chi1 to the 16 minus p. Okay, because when I tensor a theory with itself 16 times, these are the primaries of the tensored theory. And the conformal dimensions simply add, so you get all multiples of 1/3 starting at 0 and ending at 16 by 3. Okay, now if you, let's denote this full set as chi mi. So mi is this number. I'm not sure why there's an I on it, should be mp probably. The point is that you can write these, but nothing that you know would predispose you to look at this particular linear combination of them. So this is now a linear combination of characters of A21 to the 16. It's one linear combination, and miraculously, it's equal to this modular invariant. Okay, any other linear combination of these chi's isn't equal to any modular invariant, but all the so many of these with multiplicities form a big vector valued modular form. That would have been the characters of A21 to the 16. But this particular combination is the character of the ICFT. And so there's a
Sunil, can I ask a question?
Please, please.
864 is larger than 744. So J of tau minus that.
But there's
Here, that's 1/3 takes care of it.
This takes care of it. So if you work out the expansion of J to the 1/3 times this, then you find that it has exactly plus 128.
Okay.
In its first subleading term, and that's the statement that there are 128 currents.
Thank you.
The currents are there. It's just the primaries are not there.
Yeah.
It doesn't have all these primaries. It has one single combination giving the full character. And this is the miracle of ICFT. This is how ICFTs work in some sense. Okay. But now...
Sunil, just a reminder, it's about 10 minutes more.
Yeah, 10 minutes is good. Now we have a way to solve, to take a coset, because this ICFT had A21 to the 16, and we can coset it by the A21 theory. So just drop one of these, and A21 to the 15 remains. So it's a little different from the old cosets where you had to embed, you had to do something like a Higgs mechanism to break the currents of the numerator by embedding some subgroup in the denominator. Here the subgroup or subalgebra is trivial because this is a direct sum. So I can just delete any one or more of these terms in my quotient, and I'm left with everything else. And the resulting, so now the familiar SU3 level 1 Vesumino-Witten model is known to have central charge 2 and H equals 1/3. So the coset theory has central charge 30 and H equals 5/3, and it's not in any sense a tensor product of anything. Okay, it does seem to have 15 SU3s in it, and it does, but it has 2 characters, and they are these weird linear combinations of the of these chi-p's, which I've essentially defined earlier. Okay, and it turns out that this pair transforms into each other under modular transformations. It's a closed set. So from a theory which should have had some of order 2 to the 16 characters, it actually has only 2 characters by this miracle, which we could have never found, but for the miracle done by ICFTs, I should mention that these kind of formulae here are not ours. These are found in ICFTs using codes. And that was a celebrated mathematical result of the 80s. But this follows from that using the coset construction. So I hope I've shown you how the coset construction inherits qualities of the coset theory, which were qualities of the parent ICFT. But this is not anymore a holomorphic or chiral CFT. It's very much an RCFT, as good as any other RCFT, with a non-holomorphic partition function that can't be holomorphically factorized. Okay, now you may say that, well, I know only the characters and partition function. Do I know the theory really? But in a way, one of my favorite papers from the 80s with Samir and Ashok, it's called reconstruction ... We showed that if you know the characters and partition function, you can work out the fusion, you can work out the modular transformation matrix. From that, using Berlinde formula, the fusion rules. From that, using other techniques of differential equations, you can compute correlation functions on the plane and torus. And although this hasn't been wrapped up, I'm pretty sure this can be used to show that Seiberg and Moore and Seiberg's conditions are satisfied. So you can actually solve this coset CFT. It's not just that it's there, but you can solve it. Okay, now one more very cute fact. Since the original ICFT had A21 to the 16 in our example, we can also take quotients by multiple Vesumino-Witten models. So we can generalize the coset construction where the denominator has product of Vesumino-Witten models. And that means just delete more than one power of this and you'll get new theories. But the fun part is the following. This is a direct product, but when I take this quotient, the resulting coset is not a direct product. It's a new irreducible CFT for any of these direct product quotients. And in fact, the resulting theories then are a family of RCFT with two, sorry, I think I misspoke. They may not all have two characters, because if I take the product of Vesumino-Witten models, I have more than two characters, but their central charges are 2, 4, 6 up to 30. And their parent theory is the original A2 to the 16 Kerr-Weyl lattice. Okay, so it's a lot of CFTs which pop out from this construction. Okay, now I'm close to the end actually. I just have to deduce some lessons from this and then I'll close. Okay, so we can generate many new RCFTs. Very nice. They have fractional critical exponents. They are non-holomorphic. So they are not like ICFTs in that very special feature of being integral or being holomorphically factorized. And they are not made of, so this shows that all RCFT are not made of minimal series of their cosets. Now, there's one slightly crazy outcome which we still haven't understood. And I talked about this in the Spenta Fest in 2017, or I don't remember, 80, whenever it was. In the novel coset relation, the denominator is supposed to be a Vesumino-Witten model. But in this paper, following our work with Gabriel, my student and I found an example which is not of that type. It appears to be a coset of the monster CFT by the Ising model. Now, this is bizarre, because coset means you embed the currents of something here in the currents of something here. Well, this has no spin 1 currents and this has no spin 1 currents. So what are we doing? In fact, Ising doesn't even have any other currents. Being a minimal model, it only has Virasoro algebra. Now, how did we even make this claim? Well, we made it in a different way. We found that the monster CFT partition function is the dot product of the 3 characters of the Ising model with the 3 characters of some new theory, which we had discovered by some other means. And so it's like chi tilde, the bilinear relation holds. And this new theory has no current algebra because this has no current algebra and this has no current algebra. What is it? We were very excited. It turns out to be the baby monster CFT with central charge 47/2. Unfortunately for us, there's a whole PhD thesis by Hearn, mathematician, on this baby monster CFT, but we certainly discovered it independently using the novel coset. And what's most exciting is that, well, it's part of our claim of families of RCFTs, which have small numbers of characters, but are not part of any minimal series. And it goes beyond our original proposal. I think it's fair to say Matthias Gabriel didn't believe that this was a general feature, but we made some, we went ahead and made a conjecture, which is not yet proved or disproved, is that you can quotient the monster by any PQ Virasoro minimal model. And we actually found examples like 2, 5 and 2, 5 cross 2, 5 and 3, 7 or 2, 7, sorry, where this works. But those are non-unitary cases. For unitary cases, we haven't been able to either prove or disprove. It's just too challenging technically. But if it's true, then all these cosets would have no current algebra. Now, why is that important? Well, generating CFT without a current algebra is a challenging task. Examples so far have been very rare, and they're a tiny step to the bigger goal of generating CFT without any extended chiral algebra. We got rid of the most obvious chiral algebra that you find beyond Virasoro, which is Kac-Moody or current algebras. So this conjecture is open. Okay, now I'm out of time, and this is my last slide before the last 2 slides before the conclusions. So let me say what we have learned conceptually. For this, I need to talk about the Wronskian index of a rational CFT. So if the exponents of the CFT are defined like this, minus c by 24 plus h, then the Riemann-Roch theorem says, and p is the number of characters, then it says that this combination minus 6 times the sum of critical exponents is a non-negative integer L, which can be 0 or any positive integer in principle. This integer we call the Wronskian index of the RCFT. It's found by just knowing the number of primaries and the critical exponents. Interestingly, the fact that this is greater than or equal to 0 is mentioned in the yellow book, but it's not identified as a Wronskian index, and its mathematical interpretation is not given. I also won't go into it. Okay. Now, back in the 80s, when we stumbled on this concept, we realized that most known RCFT series have L equals 0. All Virasoro minimal models have Wronskian index 0. All SU2K for all K Vesumino have L equals 0. All Vesumino-Witten models for any algebra, simple algebra at level 1 have L equals 0, and the list goes on and on. There are also some Vesumino-Witten models which don't have L equals 0, but most do. And this seems to have led to an assumption that perhaps the Wronskian index is a thing we are wasting time on. It's just 0. Why are we even bothering with it? There have been several papers by very reputed people either stating or assuming or implying that somehow L is 0. And it's an important question to settle, and we've settled it. The tables I showed you earlier, you can calculate L for them, because after all, I've given you the table of primaries and their dimensions, and you find one of the tables I showed had L equals 2, another one had L equals 6. So CFTs of non-zero Wronskian index certainly exist, but you don't find them easily by looking in the usual place, but you do find them easily by taking cosets of ICFT. And here is a kind of punchline which I like. L is unbounded above, and we can find examples with arbitrarily large Wronskian index. So I would say most RCFTs are yet unknown to us, and you could call this the mathematical dark matter problem. It looks like all the things we know are a very small subset of all the things that we don't yet understand. Okay, now I'm out of time, so I'm happy to skip this. I just want to say that we have examples of cosets where I'll just focus on the last line. We have examples of cosets where, because the parent ICFT, there were 5 different ICFTs with different current algebras with the same character. The cosets are also 5 different coset theories with, let's say, 4 characters or 3 characters or 4 characters, central charge 21, and 5 different current algebras. So this decisively settles the question, can RCFTs have more than one theory for a given set of characters? So the characters of all these 5 are exactly the same, but they're 5 different conformal field theories. So again, that claim in the literature that you don't have multiple CFTs with common partition function is just not correct. Okay. Fine. Okay, I think I better skip this. But I think this, yeah, I'll skip that. I think I'm out of time. But if people want, they can ask. Let me just give a brief set of conclusions. So the novel coset construction is a useful relation. It helps us find new RCFTs by combining lattice CFT or more generally ICFT and Wessel-Witten models. They provide lessons for generic CFT. Finding a modular invariant partition function does not imply a CFT exists. In the slides which I skipped, I actually showed an example of that. Also, multiple CFTs can have the same partition function, but different correlators. And I showed different current algebras, they're different theories. So everything will be different about them, except for having the same partition function. Okay. And in some work I'm doing with Rahul Poddar, which is to come out soon, we showed that this bilinear relation is not just true between characters, but also between conformal blocks. That makes the coset relation a more powerful statement, not just about characters, but about theories. This is a bit challenging, a lot of group theories involved, and we're finding it difficult, but we might eventually, I think we have nailed some of the simplest cases. Okay, good. Now, what can we do with these theories? Maybe they can be applied to new types of quantum Hall phases or anyon physics, because there people do look for simple CFTs with simple fusion rules. But these have different conformal dimensions from the well-known CFTs. And maybe that's interesting for physics, I don't know. Another thing which is related to Suresh's question, we only considered bosonic CFTs, but supersymmetric ICFTs are known. And the supersymmetric novel coset is an entirely open question to my knowledge. So I'll stop here. Thank you very much. Happy to take questions.
Yeah. Thanks, Sunil, for your talk. So we can have some questions.
Can I ask?
Can I ask a question?
Sorry.
Sure.
Oh, Spenta, go ahead. I'll ask after.
Sure.
Okay. Sunil, this very interesting talk. This Wronskian index that you talked about, does it have some topological meaning?
Yes. It's actually
yeah. Can you?
Yeah. Sorry?
Can you please explain a little bit?
Sure. It's actually the number of poles in the modular differential equation. That's one way to say it. The number of poles in moduli space. So there's actually now I wish I had a whiteboard to write on, and I do, but it will take too much time to connect. So there's this whole story of modular linear differential equations, which are obeyed by the characters of all rational CFT. Now, the problem is that there are two ways to write a modular differential equation. One is to write it as f of tau d to the p of tau plus all subleading terms equals 0 on the character. And the other is to divide out the leading function so that it starts with d to the p and then all subleading terms. The latter way is called a monic form. In the monic form, the coefficients in the series can have poles. And the Wronskian index L is the largest, the maximum number of poles of those coefficients. So it's also the number of zeros of a particular Wronskian of the characters. So it's a complex analytic concept. It's just a number of poles basically. And Riemann-Roch theorem, which is actually as you know, people say just Cauchy integral formula, in fact, dressed up a little bit, says that poles are number of poles minus number of zeros is equal to the dimension of your modular form. And that's all we used.
See, so can I just continue a little bit? I asked this question because if you have, if you look at the idea of theory space, which was introduced in the early days by Zamolodchikov and others, then you can talk about flows between conformally invariant points. And so in some very simple cases, you can characterize the topology of the space of those flows.
Right.
Now, is there some such similar thing that if you have a particular Wronskian index, fixed one, that those theories will sort of flow into each other, or
that's
some such idea?
Very nice question. It's totally unexplored. Actually, I must say it's been a struggle to convince the community that Wronskian index even is a thing. I mean, the whole 1,000-page book of Di Francesco doesn't mention it even once. It's just not a thing for them. And So, if people would look at this, yes, one could take, for example, a theory with Wronski. So we know theories of Wronski. So I should also say that we know a lot about two character theories. Okay. And we know them for Wronskian index 0, 2, 4, 6, 8. I mean, it's easy to construct lots of them. So we could ask the question, take one of them, perturb it, and find out what happens in the flow. My impression from Zabolotshikov's paper is that you lose some primaries, right? He goes from some higher minimal model to a lower one. So the number of characters would actually change. So it would that would certainly upset the Wronskian index. So there's no reason I can see why it should be or should not be an RG a flow invariant. It's a very good question, because after all, that and the central charge are the two things which we think are the most important characteristics of a CFT. The difference, though, is central charge is not integral. But Wronskian index is integral, so I don't know how it would flow.
Yeah,
that was a long answer. Short version is I don't know the answer.
But the flow, Sunil, I think what Spencer said might be still true, because I mean, you said the minimal models all have L equal to 0, but you do flow from one minimal model to the next.
So it can be preserved, yes. But whether L not equal to 0, so L equals 0 can't go anywhere because there's nothing lower for
sure. Yeah.
Well, you can go to trivial theory, right? C equal to 0.
Yeah.
I mean, Ising model, if you perturb, we will eventually flow to C equal to 0, which also has L equal to 0, I think.
Yes. Okay.
Yes.
Yeah. So in a sense, known examples, at least in this context, seem to be following that. But I mean, okay, if this is true, then that will tell us that if you have a L not equal to 0, right, then you will never be able to flow into trivial theory, which seems unlikely. That you should be able to perturb it. I mean, as long as it has a relevant perturbation, right?
But yeah, good point. But that's part of the fun, by the way. I think it's not. So as you say, either it will flow to a trivial theory or it can't. And if it can't, there better be some reason in terms of absence of the right perturbations. But one of the interesting features of the L not equal 0 theories we have found is that their conformal dimensions left and right are typically greater than 1, which means that the primaries are all irrelevant operators.
I see.
Now, of course, you also have currents which are marginal, and I don't know how much is known. I'd love to talk to any of you about this, about say JJ bar perturbations of these theories. You can certainly do that. At least it's marginal. Whether it's integrably marginal or not, one has to see. But there are no, all the Wessumino-Witten models, I think, always have a primary of dimension less than 1. I think that's a feature of Wessumino-Witten models. It's certainly a feature of Virasoro minimal models. And so all of them can flow down, but then these are also the ones which always have L equals 0. So there's a very interesting open question here, whether L can change. And as you said, Ashok, either you reach the trivial theory with C equals 0, or you reach some theory which is almost trivial but has L not equal to 0. I don't know what happens. Or you can't,
which is the end point of a flow, that you cannot flow from there anymore, right?
Yeah. Which of course is very interesting, because endpoints are obviously more interesting than, are obviously very interesting. It's all very exciting, and I keep saying this and sounding a little pathetic, but nobody works on this. So it's not like we are seeing people who work on this are somehow always trying to aim it to the ADS CFT. And actually something I'm working on also now is to see what RCFTs can teach us about ADS CFT. The naive answer is nothing, but a lot of people are claiming recently, we've heard talks by Perlmutter and other people, Nathan Benjamin and so on, and they do seem to think that RCFT can be helpful in some way to study semi-classical ADS3 holography. But these other questions in RCFT, I think, are fascinating from point of view of RG flow. So yeah, that was a very good question, set of questions.
Thank you.
So maybe one more quick question. Suresh, I think, had a question. But
no, it had to do with the nomenclature of Wronskian. So it comes from the differential equation. Right? So suppose I did things like Mason, which is to say that I write everything with Q power, just looking at from differential equation viewpoint, adjust the indices to lie between 0 and 1, then you can show that the Wronskian of the vector valued modular form will be delta, which is eta of tau power 24 to some power. Is this that power?
I wonder, it might be. I've forgotten how Mason did it, but it seems that, okay, you're saying rewrite the differential equation so that the character, by absorbing some etas?
Yeah, you could do that. Yes.
But are you sure that these people are not doing L equals 0 theories? Because in
not necessarily, I think.
They just start off writing the differential equation for L equals 0 and then they just often go home with that. I never understood that.
Okay. No, but the Mason's work is very old. I mean, there's newer work by Cannon et al., which take care of more general things.
Yeah. Actually, I followed some of the new work of Gannon. That's quite interesting. Mason also, I've been in correspondence with him. But for example, one thing that he was doing was classifying 3 character CFTs with L equals 0, which is something that Samir, Ashok and I partially did. And then Samir and Ashok have a paper where they actually completed it. And I had forgotten about that paper. But then these people are now trying to find some more. And so that's, but they're all only working on L equals 0. I haven't seen any paper in the maths literature which is on L not equal to 0. I don't think I've seen even one.
Okay.
So, Prithvi, could I ask a question? I had my hand raised.
Sure.
Okay. Yeah. Go ahead. Yeah.
Yes, Sunil, you said that this ICFT is nice talk, by the way. The ICFT you are modding out by this Vezumino, which is a trivial factor in the group. But what if you embed non-trivially one of these modding? Do you get something new?
Yeah, I think so. It may not be so, it definitely you'll get something new. So for example, I don't see why you can't mod out my A21 to the 16 theory by A11 Vezumino instead of A21 by fitting the A11, that is the SU2 current, as a subgroup of the SU3 current in the numerator. Now SU3 over SU2, I forget right away, it might leave a U1 or something. So you'll get a theory which has SU3 to the 15 times U1. That's also new. Yeah. I think
actually, I had in mind something like embedding one of the SU3s as a diagonal into SU3s, yes, because you have several of them.
Also you could do. Thank you. Yes. No. So there's a lot that could actually it would be worth exploring the most general thing you can do because that's never been done.
Thanks.
Okay. So if there are more discussions, we can move it into Slack. So
okay. I'm not on the Slack, but if I don't probably know how to do it or I have not done it. But if someone wants to chat, please just email me and I'll be happy to chat.
Okay. Thanks, Sunil.
Thanks.
So the next speaker is Professor Sujay Ashok from IMSC. Maybe I can ask him to screen share. If you stop the screen share, Sunil.
Share the screen now.
I've stopped the screen share long ago, actually.
Yes. Yeah. Okay. Fine. Yeah, it's visible. So, yeah, as I was saying, Professor Sujay Ashok from IMSC talking about surface defects from fractional branes. Over to you, Sujay.
Thank you. Thanks to Suresh, Tanay, and Ayan for the invitation and for all the organizational work. So, thanks to Sunil for a lovely talk. I'm not sure if I'll be able to keep up with the same standards, but I'll try. So it's going to be very light paper in some sense, or light talk in some sense. So the topic is surface defects from fractional branes. Okay, so this is work done with my collaborators from Italy, Marco Billo, Maria Luisa Frau, and Alberto Lerda, and with my student Sujay Mahato here at Math Science. It's based on these 2 papers. But I'll mostly focus on what was done in the first paper and just make some few comments about what was done in the second paper. So the topic is to understand surface defects in the context of string theory. So what I'll first do is to review surface defects in N equals 4 as it was first formulated by Gukov and Witten in 2006. And then I'll sort of summarize what the main goals of this talk will be. So the main goal will be to just embed this surface defect in string theory or somehow geometrically engineer it And the setup is not new. It was already known 10 years ago, but we'll see what we can add to it. And the basic idea is to calculate some string amplitudes and show that whatever physical properties that Gokam wrote down in 2006, one can recover using string perturbation theory. So then I'll end with some simple checks of this proposed plan. And also please interrupt me if there are any questions. That will be helpful. Okay, so let me begin with a sort of longish review of surface defects. So these are codimension 2 defects in gauge theories. So these are natural generalizations of Wilson and 't Hooft line defects. And we'll restrict ourselves to just those to half BPS defects in n equals 4 superangles. And so topologically, you can have different configurations, I guess, but in the half BPS case, we'll just consider planes inside R4. So they're extremely simple. And these were introduced by Witten and Gukov, like I said, and they refer to them as monodromy defects. So I may not explain why they call them monodromy defects. So here I've shown you the two plane that is transverse to the defect. So the Z is a two plane transverse to the defect. And R and theta are some spherical polar coordinates here, or just polar coordinates here. And you see that you define the defect by specifying what the 4-dimensional fields behave as you approach the defect. So the defect is located at Z equal to 0. And so these profiles of the gauge field and the scalar field, they show that there is a singularity there. So phi has a simple pole there. And if you compute the field strength from A, you will see that it is a delta function source at the location of the defect. So so in this way of defining it is very similar to how one would define an 't Hooft loop. You specify the 't Hooft loop or 't Hooft defect by the profile of the gauge field as it approaches the location of the defect. So you can see that there's a non-trivial holonomy of the gauge field as you go down this circle in this Z plane. So you call these monodromy defects. So I've been very schematic here with alpha, beta, and gamma. So if you have a generic defect in UN Yang-Mills theory, what this is shorthand for is this. So here I've so the d theta and the 1/2z are still the same, but the alpha has been written in full glory with the Lie algebra indices clear. So you see that the gauge group UN is broken to a subgroup at the location of the defect. So there is some UN0 to UN-1. And each of these matrices are block diagonal. And these alpha naught, alpha 1, and alpha n-1 are this real parameters. And here I have beta and gamma similarly. And it's the same breaking. So these IN naughts and IN are the same in both these profiles. And they're just n0 by n0 unit matrices. So I hope the configuration is clear. The defect is specified by this singular profiles for the gauge field and the scalar. I hope this is clear. But because, so we can show that these profiles, we just put these into the supersymmetry variations. You can show that these preserve Poincare and conformal supersymmetry, so they're half BPS. And these n's that we discussed here are just partitions of capital N. So alpha, beta, gamma specify the singularity of the gauge field and the scalar. Okay. But because we are in 4 dimensions, and because the defect is codimension 2, so the defect is 2-dimensional, you're allowed to turn on some 2-dimensional theta parameters on the world volume of the defect. So if you're doing a path integral, you do the path integral over all gauge fields and scalars with the prescribed singularity of the defect. And in addition, you can turn on, you can add this term to the action, which is 2-dimensional. So this trace F is over the U and I factors that are left unbroken at the defect. Okay. So the takeaway from all of this review is that the Gokam defect is characterized by some discrete parameters, which is just a partition of N. And this is very similar to how the Wilson and 't Hooft loops are classified by some representation. There's some discrete data that classifies the defect. But unlike those cases, you also have some continuous parameters, alpha, beta, gamma, eta, that sort of go into the definition of what the defect is. Okay, so this is the defining data of the defect. Are there any questions here? Okay, so let me go on. Good. So the last property I want to review, which is also written in the original paper of Cook and Mitten, is that these parameters have well-defined transformation properties under the S-duality group of n equals 4. So it's well known that n equals 4 has this non-perturbative S-duality group, SL2Z, the modular group. And these alpha and eta parameters act as a doublet under this SL2Z. They transform like this, as a row vector, if you wish. And beta and gamma are scaled under the action of S-duality. And this tau is just the usual complexified gauge coupling of n equals 4. So this concludes my review of all the properties that I want to talk about as far as the defect is concerned. So let me tell you what we will do in this talk. So my goal is to embed this defect in string theory. So it means that I want to engineer using some D-branes in type 2B string theory, all the properties that we just saw, which means that we would like to derive the profiles, the singular profiles of the gauge field and scalar using some worldsheet analysis. If I realize the defect as some fractional branes in some type 2B string background, how can I derive these scalars, the scalar and gauge theory profiles? And at the end, we will check a proposal by showing that however we realize it, when we recover these profiles, all that will be consistent with this S-duality property that we just discussed. So this will be the consistency check, but most of the talk will be just trying to set it. Okay. All right. So let me tell you what the setup is. So the setup was known back to it was known by Kano and Tachikawa back in 2010. So what they did was to consider a sort of NI stacks of fractional D3 branes of type I on the following ALE space. So they considered the orbifold background. Now note that the gauge theory is realized by the D3 branes. Okay? So those are extended in the C1 and C2 directions. So those were blue directions. And the orbifold, usually you consider D branes transverse to the orbifold. Here, the D branes are extended, partially extended along the orbifold. So the orbifold is along 2 and 3 directions, complex 2 and 3 directions. And the D3 brane is along 1 and 2. So this green direction is sort of along the D brane, but what will turn out to be is it will be transverse to the defect. So the defect will be realized along this first complex plane, what I call these parallel directions. And these two directions will play the most important role, but they are the directions of the D brane that are along the D brane, but also along the orbifold. Okay, so such branes have been studied in the past, but not to the extent that the fully transverse branes were studied. Okay, so this is the setup. And Kano and Tachikawa discussed this configuration already back in 2010, but they did not derive the profiles that I talked about earlier. Their interest was from the context of computing instant-on partition functions. So what they did was not just consider D3 branes, but also D-1 branes that act like instant-ons for the D3s. So they considered both D3 and D-1s, fractional branes, in this background. And they studied the spectrum of all open strings with at least one leg on the D instanton. And then they wrote down an effective action for these D instantonic moduli. And they showed that it was an orbifold of the usual ADHM moduli action. And they used it to compute the partition function of instantons in the gauge theory in the presence of a defect. So what they showed was that the instantons sort of fractionates, and you have these fractional powers of what used to be the full gauge theory instanton. And a lot of work has been done in this regard. And especially interesting is work by Jeong and Nekrasov, where they started off with this instanton partition function in the presence of the defect, and they showed that you could sort of analytically continue this contour integral that one gets to other realizations of defects as flavor defects. But our interest will not be this. We were always puzzled by why this orbifold, is mimicking a surface defect. So what we want to do here now is to ask, in what sense does this configuration of fractional D branes on an orbifold describe a surface defect as we understand it from the gauge theory? And what we're going to do in this, what we did in this work is to recover the profiles of the gauge field and scalar from this string configuration. So if the question is a good point to pause and ask. Just drink some water in the meantime. Okay, there are no questions. Let me get back to the talk. So if there's a profile for these open string fields, it's natural to assume that there must be some source. Let me explain this point, and I'll explain it in the most basic terms. So suppose you have some open string field, and suppose there's some source for the field. Then the equations of motion, the classical equations of motion, would take the following form: box phi, some massless field, is equal to the source. So if someone gives you the source, it's very easy to read off the profile that the source will induce by just doing a Fourier transform. So you can solve this equation in Fourier space and divide by the box in Fourier space, and you will get the profile of the field you're interested in. So if there's a profile, it's natural to think that there must be a source for these open string fields. And so what is the origin? What could be the origin of the source? And recall that our setup is some fractional branes on some orbifold. So it must be that there's something particular to the orbifold that acts as a source for the open strings. The new states that exist for the orbifold that are not there in the flat space theory are these twisted sector states. Okay, so logically, it makes sense to think that there must be some coupling between the twisted sector states and the open string fields, and that perhaps you're giving some background values to these closed string fields, and these act like sources for the open string fields. So this is what we assumed. So we assumed that this was the mechanism. So we turned on some constant background fields for some scalar fields in the twisted sectors. And we computed this open closed correlate. So, so there's some disk amplitude we are computing where there is some D3, this fractional D3 brane boundary conditions that are imposed on the disk. We have one insertion of this twisted closed string field and one insertion of the open string field you're interested in. And we turned on expectation values for all of them to see which ones couple, which ones don't. And if this indeed is the source, if you follow what I said in the previous slide, if you did the Fourier transform, you should recover the the profiles of Gukov and Witten, and this is in fact indeed what we find. And some combinations of these background values for the twisted scalars will be identified with these parameters we introduced at the beginning, these alpha, beta, gamma, and beta. Okay, so this is the mechanism at work when you want to realize defects in string. Okay, so I just want to make a few comments. First of all, this is not a radically new idea. Similar ideas were used in the past. So for instance, once the boundary state formalism was written down and D-branes were first formulated, these people showed how to obtain the leading correction to the profile for gravitational fields around the P-brane soliton using this similar method. And more close to what I'm doing here, the classical gauge profile of the instanton, the profile of the classical instanton was also derived in the same way by using D3 D-1 system in flat space. On all the examples, they essentially share the same idea that there is some world sheet with either closed or open insertions that acts as a source for a particular open string field. And then from the classical analysis, as I said, the Fourier transform will give you the profile for the field that you're interested in. So lastly, I just want to say that it's always worthwhile to embed field theory solutions into string theory, because usually you've always learned more. So classic example is this Sabbe-Witten solution of SU2 gauge theory. The moment it was embedded into into a string theory context by Witten, where he showed that it's essentially an M5 brane wrapping a curve, the whole sort of whole other area opened up, all these class S theories came up, and nu n equals 2 dualities came up. So, so I feel like it's always worthwhile to lift field theory solutions to string or M theory. Okay, so now that those were the introductory / context remarks. But I hope the basic mechanism is clear. This is all that we do. Concretely, what we do is to compute such a correlation function on the world sheet. So we take one of these closed string scalars, we take the open string fields of interest, and we compute this in the presence of a particular D3 brane boundary condition. So essentially what you need is a twisted closing spectrum of the orbifold. This has been known for a long time, since the early 90s. The open string spectrum on these kind of fractional branes partially extended along the orbifold is new, and so I'll spend most of my time here. And lastly, we also need the boundary state that essentially tell you how the closed string fields are reflected at the boundary. So once you have these inputs, it's just standard superstring perturbation theory. So I will not mostly give any details. I'll just give you what the setup is. Okay, any questions at this point? Okay. All right, so closed string theory on the orbifold. So as I said, this has been known since the early 90s, and deep branes on the orbifold was first studied by Douglas and Moore, and I'll briefly summarize their results as to what the closed string fields are. So the isometry group of this C2 is SO4, and if you write that as SC2 plus times SC2 minus, it's two SC2s, the orbifold group is embedded into one of the SC2s. So essentially all the fields that you have will be representations of some SU2, of one of the SU2s. Now, what we have in addition is a D3 brane that is extended along the orbifold. So in fact, this isometry is broken, and all we have is really an SO2, which is just the rotation along these planes. Okay, so this is my summary slide for the closed string states. So the bottom line is essentially what is written on the bottom line, which is that there are four twisted scalars from the NS sector and 2 scalars from the RR sector. This is what we find in each twisted sector, and for Z2 there's only a single one. We find 6 scalars, and you can see that these came from the singlet and triplet fields. This is triplet another SU2, which was there before you introduced the D-branes. Singlet and triplet of the SU2. So essentially, once you introduce a D-brane, you just split them by the splitting of these Pauli matrices. And these V and V tilde are the left and right moving fields, and they are given here. I will just mention that this is the superghost as the superghost sector. This delta is the ground state of the twisted sector. This is the bosonic part, and this fermions become spin fields in this orbifold. So the NS scalars are SO4 spinners, and the RR sector are SO6 spinners. So I don't want to go into the details here. I just wanted to show you that it is explicitly known what the vertex operators are. And these 2 scalars, one of them was always there. It's the Ramond scalar. The other one descends from what used to be a 2 form in the theory before the D-branes were introduced. Okay, so there are 6 scalars. Very good. What about the fractional branes? So fractional branes are labeled by the irreducible representations of the full group. Again, this has been extremely well studied in the string literature. For Z2, there are 2 types of fractional branes because the 2 irreducible representations of Z2. And for Z2, in fact, the fractional branes that we are interested in, where it's partially extended along the orbifold, they were already written down by Bertolini, Di Vecchia, and Marotta in 2001. Essentially, each fractional brane has some. So the boundary state tells you the couplings to the closed string sector. So there's some part that tells you how the couplings are to the untwisted fields in supergravity, and this part tells me how the D-brane couples to the D-brane sources the fields in the twisted sectors. And Z2 is so simple that this just depends on a sign. The 2 types of branes just differ in a sign as to in the twisted sectors. So what we want to do is to take N0 and N1 stacks of these 2 types of fractional branes, and what we already know is that from here that the twisted sector states I'm interested in are essentially spin fields. So all you really need are this is the ground state part of the boundary state. And from the boundary state, what one does is to derive the kind of reflection rule. So let me just give you pictorially what one does. So here we have this boundary state on the disk. You do a conformal map to the upper half plane. So this is the picture that you get. And you have some boundary condition here for the D3 brane of interest. And essentially what you can do is to translate that to a reflection rule for the right movers, do the doubling trick, and then essentially what you have is a 3-point is equivalent to a 3-point correlation function for the open strings. For just the left moves. So everything is completely explicit. I've given you the explicit reflection rules that you can derive from the boundary state for the states of interest. So it's just a matter of doing the computation. The last ingredient is going to be the open strings, and here we find something new. So usually if you have Branes that are completely transversed to the orbifolds, what you do is to write down the open string vertex operators. You have oscillators, you have chant pattern factors, and then you keep the combinations that are invariant under the orbifold action. So depending on if you have an oscillator with a field that is charged under the orbifold, that'll that won't be an adjoint field, it'll be a bifundamental field in this fractional Branes patch. But because we have brane directions along the orbifold, the new point is that the momentum factors that you have are also charged under the orbifold action. So for instance, instead of plane waves, what you have to do is to consider sine and cosine combinations. So you can see that cosine is invariant under the orbifold, and sine is picks up a sine under the orbifold action on Z perpendicular. So in fact, what you have to do is to consider oscillators, chant pattern factors, and momentum factors. Okay, so if your open string state contains momentum modes along the orbifold, then you have to do this process. Okay? I hope this point is clear. And so what you find is that exactly as you would expect, no open string state is projected out if it carries momentum along the orbifold directions. Okay, you can always find the momentum factor, a suitable combination of plane waves in the ZM case that will cancel the extra charge. So what you find is really n equals 4 with an additional 2D sector. Okay, so in the papers, we don't really go into this in detail, but it's something that we are working on. We can really show that also from the one-loop partition function that there's a 2D sector and a 4D sector. And it really is a defect in n equals 4. Okay. So now that we have everything in place, we have the vertex operators. So yeah, the open string vertex operators I haven't shown you yet. I'll show it you in the next slide. But modulo that, we have everything in place, and we can just compute this disk correlate. So notice that since this is the disk amplitude we have to compute, we only need really for this computation, all we need are the open strings that have diagonal chant pattern factors, because there is no other insertion here. So it's even simpler than what I just described earlier. So I've just shown you an example of an open string vertex operator that we have in the zero picture. So why the zero picture? Because I don't know if you remember, but the closing vertex operators all have total picture number -2. So that also already saturates the picture number on the sphere. So we need to write down the vertex operators of the open strings in the zero picture. So you see, this almost looks like what we know from Polchinski, for instance. But instead of plane waves, what you have are these sine and cosine combinations in the perpendicular directions. And that's because these fermionic bilinears are either charged or uncharged under the orbifold action. So depending on that, you either have to couple it to a sine or a cosine function. Okay. So these, for instance, are this is the gauge field component A1 along the defect. It's some complex notation I'm using. A1 is along the defect and A2 is transverse to the defect. Okay, so you have everything in place, and these 3 dots, as I say, these semi-computers in string perturbation theory is much above paper, and everything is completely standard. We have decoupled free theories on the world sheet, and this is some sample correlators in each sector. So in the super ghost, we have this correlator. In the bosonic directions, we have no other excitations because you have twist fields in the closed string sector, so you have a momentum conserving delta function. Bosonic, again, sector along the transverse directions is also known. And the only non-trivial part is really some non-trivial gamma matrix algebra, but this technology goes back to Friedan Martin-Schenker in the mid-80s. So everything is completely standard. So let me just give you the result. Okay, so after doing all of this, what we find are the following couplings. Okay, so we find that the gauge field component A2, which is transverse to the defect, but of course along the brane, couples to the singlet NSNS field. So this B is the expectation value that we gave, or the background value that we gave to the singlet of the NSNS sector. B plus is the charged field, charged doublet in the NSNS field. That couples to the open string scalar, only to one of them, exactly as in Gokon written. And the gauge field along the defect, the components along the defect couples to the Ramon-Ramon scalar. Good. So let me make a few comments. So remember, we started with 6 scalars, but only 4 of them appear here. Okay? There is no coupling to the B prime and the C prime scalars. The other 2 scalars, C prime descended from this 2-form field, and B prime was the third component of what used to be the triplet in the orbifold theorem. As expected, the momentum conserving delta function is only along the defect directions. And you see that now clearly as we anticipated, the twisted scalars source the open string fields in the space. So all that remains is to read off the profiles of the fields by doing the Fourier transform. It's also easily done. In fact, it's particularly simple because the couplings that we found are all proportional to the momenta here. So this kappa 2 is just the complexified momentum that I introduced earlier. It's the complexified momentum along the in the direction transverse to the defect. So it's just a very simple computation. You essentially find a pole. So every momentum factor here translates to a factor of 1 by z or 1 by z bar in the transverse directions to the defect. So if we take care of all the factors, what we find is that the gauge field transfers to the defect has this particular profile. So if you compute the same thing for the complex conjugate and form the one-form gauge field, you find exactly the d theta type term that I introduced at the very beginning. So clearly B, the background wave of the NSNS singlet scalar, is what I call alpha initially, up to some factors. The same thing we repeated for the scalar profiles. Again, I get the simple pole expected. And this is just for a single fractional brane. If I take n0 of one type and one of the other, because the twisted fields have this simple sign flip in the boundary state, all you find is this sign flip here. Okay, so we exactly reproduce the expected singular profiles for a mononomial defect of type n0, n1. Okay. All right, so now let me go to the one profile that we did not discuss, which is the Ramon-Ramon one. And initially it looks to be 0, see, because there is a momentum conserving delta function along the direction of the defect. And I also have a kappa 1, which is the complex momentum along the same directions. So indeed, there is no source. So there is no source for this gauge field. But if you think a little bit, you'll find that in fact, what this coupling is telling you is in fact, what this disk amplitude is giving you is a coupling on the world volume of the defect. And it's indeed the theta term that we've been looking for. If you're careful about all the factors, you put in the right combinations, what we find is that if the field strength is non-zero along the defect, right, then this coupling is non-zero. So then this coupling is indeed non-zero along the defect. So if you Fourier transform exactly as usual, what you find is a coupling that is localized at the location of the defect. Okay, so there's only non-zero if this integral is non-zero. So we are basically done. So in the path integral, what this essentially means that we have the freedom, if you turn on C, to introduce this. I mean, if you turn on C, you will induce this 2D theta term in the path integral. And so we have done what we set out to do, which is to map alpha, beta, gamma, eta to something intrinsic to string theory, which are the background values for all these 4 scalar fields in the closed string twisted sector. All right, so now let's do the check that I promised. Consistency with the S duality. And here I have to thank Ashok for an email that I wrote to him. He was very kind to respond. And what we realized after his email was that if you blew up the orbifold, what you essentially have is a smooth ALE space. And there in the smooth ALE space, it's well known what the low energy degrees of freedom, how they behave under S duality. So all we have to do is to make the map between the twisted scalars that we have and the low energy fields of supergravity in a smooth ALE space. And this already was also well known. So for instance, the NSNS singlet field B and this Ramon-Ramon scalar C that we had, they indeed can be identified with the periods of the B and C, NSNS and Raman-Ramon two-form fields over the now non-vanishing cycle of the Ailey space. And so if I just compose that map between alpha and B and these two fields, we find that alpha and eta essentially these period integrals of these NSNS and Raman-Ramon two forms. And their behavior under S-duality is well known from the early days. So they indeed transform like a doublet under SL2Z. And one can check that this exactly reproduces the expected transformation that Cook and Witten had in their paper for alpha and eta. Exactly the same way, the B plus minus, what used to be part of the triplet field, they are the complex structure moduli of the Ailey space, and they are essentially metric moduli. And the string frame metric transforms like follows under S-duality, and is essentially beta and gamma parameters. I should say, I forgot to mention, I should say that in a completely different context, where these surface operators were realized as holographic surface operators using some, not just probe B3 branes, but using some back-reacted geometries. Exactly the same maps were found by Gomez, Matsuda, and Drucker. But of course, these are not in an Ailey space. They have some, back-reacted in ADS 5 in the SY space, and these are some non-trivial cycles there. But the map looks the same. Okay, very good. So I think we have had we have done what we have promised, and we have checked our proposal. Let's consider with S-duality. But so far, all I've discussed is the simple Z2 orbifold, which is just the defect with two partitions and not in N1. One can do this for the ZM orbifold as well. It gets technically much more involved because the generic defect is labeled by all these partitions and all these 4n parameters, if you wish. All the conceptual ideas go through exactly as in the Z2 case. But the technical difficulty is that the twisted sector scalars are not ground states anymore, but they're now excited states. So there's some it's just more involved to compute all the discorrelators, but we did it and everything goes through. Again, the open strings operators are more involved because it's not just sine or cos, it's some complicated combination of plane waves, but again, it goes through. And now the map is not just alpha is B, but the map is really this, it looks like this. And if you're familiar with deep and orbifolds, this is not an unfamiliar equation. It's essentially telling you how to go between the conjugacy classes, which is what label the twisted scalars, with the closed string fields, and the irreducible representations, which is what labels the fractional branes. So, it's a completely natural thing to have such linear changes of coordinates between these. Let me just see if I missed anything. Yes, I don't know if right, I forgot to mention one point here, which is that unlike the Z2 case, the B prime and the C prime fields, which did not couple to the open string fields, now they do couple in the ZM orbifold. So in principle, one could have a more general defect where these are also turned on, but those will not be consistent with S-duality. Because B and B prime combine linearly to give the alpha parameter. So if you want to match Gokak-Witten exactly, then we have to turn those off. So the Gokak-Witten defect is that which is, it maps to exactly the singlet being turned on and the two-component doublet, with the third component not being turned on. So I should have mentioned that here, but I didn't. But okay. Okay, let me end with some final remarks. So this is sort of the geometric engineering that I promised at the beginning. The main takeaway is that the background values for the scalars map to the alpha, beta, gamma, eta parameters of the Cook-Witten formulation, and we could recover singular profiles. And more importantly, I feel that this gives us a framework where now whatever questions you can ask about defects can be asked now in the string theory context, and you can ask, can you ask questions in string theory that you could not have asked in just a purely field theoretic context. So I hope to explore these things in the future, but for now, that's it. Thank you.
Thanks, Sujay, for the nice talk. We have time for questions. Any questions? You don't need to type it out, you can just ask. Okay, when we are waiting for others. Can you speculate what kind of use you
Sorry,
can?
I cannot see the comments because I'm in full screen mode. I can't see
No,
anything.
no, that's fine. I think people can ask questions directly.
Okay.
Yeah. So can you speculate what kind of, some dualities or something that you can extract just for field theory from this?
No, not at the moment. I'm still
Not at
in
the
the
moment.
process of exploring these things.
Okay.
Yeah, it would be nice to make use of this framework to ask some new questions.
Yeah.
But so far we don't have it.
Oh. Any other questions? Okay. If not, let's thank Sujay again.
Thank you.
So this brings us to the end of the session. The last talk had to be cancelled for some reasons. So the next session will start at 2 o'clock in the afternoon. Is that right, Anne?
Yes.
Okay, so let's end the session.
Thank you, Prithvi.
Over to you, Anne. Yeah.
Thanks to all of you, and see you back in some time.